Welcome. Today we're going to take a look at recursion using Java. So we've got a couple of vocab things you want to watch for as we're working through this. We've got, of course, the base word recursion, base case, recursive case, the infinite case, Stack Overflow, our favorite website, integer overflow, and breadcrumbs. These are some terms you should listen for or watch for as you're actually going through and working with recursion. So what is recursion? The strict definition, of course, is defining a method with itself. Now, that's not really the most helpful way to look at it, but let's go into a bit more detail. So it's a problem where the solution for the large problem is the exact same as the solution for the smaller problem once we get to the small enough solution. Now, we want to keep in mind that when we're working with recursion, everything that can be done recursively can also be done iteratively. It might change the code or how much we have to write for that, but every recursive solution can also be done iteratively in a different way. Now, when we're using recursion, we have an implicit data structure we use to maintain the information that we actually solve the problem with. And that is the stack of calls for that method as we go through and recursively call it. And they get built on the stack, which maintains the order and control flow of that actual problem. There is a potential for algorithmic elegance when we're using recursion, but it can also be weighed down by the efficiency and or structure for following through the code we're working with. And you can also use helper methods that recursively do the work for you to make that abstraction even easier. And so let's go ahead and take a look at some of the details for that. So the first thing we want to take a look at is the idea of a base case. So this is when recursion has to stop. We've actually solved the base part of the problem. You must have a reachable part of this, otherwise you're going to have infinite recursion and you don't have anything happen. And this is based on the parameter or parameters of the method you're sending to that. That's how we identify when to stop. And then when we get to the stopping point or the base case, that's when we give the answer that we finish off with. Then we go back up and we do the rest of the solution as we go through that. The next part we have is the recursive case. What do we do when we have to keep calling that same method? So we're going to call the method again with a modified parameter set. This generally should shrink the problem. Now, yes, you theoretically could use recursion to make the problem bigger and bigger and bigger until you get some arbitrarily big idea, but that really doesn't actually help us solve the problem really well. So we start at the big spot, we break the problem down until we get the smallest case, and then go from there and then reuse that to get back and actually solve the original problem. The modifications we give to that parameter are how we make it eventually approach the base case, aka the stopping point of a recursion. And we do want the execution to actually stop. We don't want to have the recursive case go on forever. That gives us problems. We also might leave breadcrumbs on the behind as we go down through the stack so we can be evaluated or used on the way back when we go back and finish processing the data from the stack. Those breadcrumbs can be an operation, they can be an execution statement, maybe a calculation, but we use those to actually go through and come back when we're coming back through, using it to generate information as we come back through the stack, processing the calls as we pop them off the top of the stack. Now, when we're using a recursive structure, we want to talk about the return type. So this is a method, of course, that has parameters, and I use an if-else inside the method based on the parameter itself, so it tells me whether I'm going to continue recursing or if I'm done with my base case. The base case for me is always going to be the if block, and it returns the value that we stopped the solution. Our recursive case says it's going to return a value based on a call to that method, may or may not have the breadcrumb like we talked about earlier, based on a changed parameter. So it should make the parameter smaller and eventually get us to that point. So the recursive structure has an if-else block inside it. The if block is when I return is just a straight value. The else block is when I return a calculation using that same method again to continue going on until I reach the base case. With a recursive structure on a void method, it's a slight different thing because we don't return anything back from that. Again, it's a method with parameters. It has an if-else block again based on the contents of those parameters. And the base case does something. What that something is could be printing, it could be doing nothing. Well, not really useful, but you can't do nothing. And then the recursive case calls that method again with a modified parameter, but instead of returning a value, it just says call it as a do this statement. And again, that statement could be just printing something, it could be doing nothing, because again, it's calling the method with a change parameter until we get to the base case, the solution part of the base case or the solution for our problem. Now, one of the easy examples we see for that is the idea of factorial. It's the product of all the numbers leading to this number, and remember that 0 factorial is 1, so that's where we're going to see our base case specifically. So we have our code, an iterative solution. We're going to loop from 2 to n, multiplying and saving the variable back into it, and the value just is times equal to index. On the math side, for identifying this as a series, we say factorial of x is equal to 1 such that x is 0, or the product of from n to k, such as k is 1 all the way up, and such as x is greater than 0. In code, we see that right here, where I have a private int factorial passing an int number. If number is equal to 0 or number is equal to 1, then I return 1. Otherwise, I return number times factorial of number minus 1. And in this case, number is my breadcrumb, and factorial, number minus 1, is my recursive call. So I have that breadcrumb of number I'm waiting to process once I get back from the stack as I go back through, once I reach the base case, and I get that value back on there. Fibonacci is also another common one we see with this, so it's a nifty sequence of numbers, aka a pattern, and it's the sum of the two previous Fibonacci sequences. So I have 0, 1, 1 and 1, and 2 is 2, 3 is 3, 4 is 5, 5 is 8, 6 is 13, 7 is 21, 8 is 34, 9 is 55, and 10 is 89. As you can see, it gets pretty big pretty fast. In the Fibonacci logic, we have an iterative solution where I'm looping back from 2 to n, adding values to the sum and swapping the values as we go. If you want to look at the actual solution, go ahead and do that. It's a great solution. In the math logic right here, I have Fibonacci of x is equal to 1 such that x is 0 or 1. Otherwise, it's Fibonacci of x minus 1 plus the Fibonacci of x minus 2 such that x is greater than 1. So here we have it in code. So my private int fib method int number, if number is equal to 0 or number is equal to 1, then I return 1. And otherwise, I have a double recursive call. I return the Fibonacci call of number minus 1 plus the recursive call of number minus 2. And this is where that problem gets so slow because of those two recursive calls that gradually get bigger and bigger and bigger and bigger as I go down through that structure. And so this is where it's algorithmically, it's elegant. However, the actual execution speed on this, not a good choice because it takes too much time to solve that problem. Now, when we're talking about Fibonacci sequence and factorial, we see that there's a problem with the actual numeric values we're seeing on here. When we're doing recursion, we experience again the idea of type overflow. We haven't seen this since we talked about math a while ago. With type overflow, we see that we have a int factorial breaks the int data type at 17. It's just too big, too fast. And overflow exceeds the bounds completely at 34. We just get to 0 and we're just done. On double, factorial hits infinity at 160 because it gets so big so fast. Even though double holds this ridiculously huge 2 times 10 to the 306th power, we get so big we hit positive infinity at 160 and you can't even calculate anything past that point. So again, when we're working with the idea of the numbers that get so big, we have to talk about overflow because that number gets so big so fast. Now, stack overflow is the problem we want to avoid with recursion. So this means we did the incorrect base case. We didn't properly actually have a value that stopped what we were working with. We were usually dealing with infinite recursion or almost infinite recursion. And so that causes it to put a stack on top of stack on top of stack. And because computers go so fast, that stack gets so big so fast that our system just shuts down and our app crashes. And that's not good. Another thing to do when you're looking with this, never do a recursive constructor call because again, you're calling the constructor, which calls the constructor, which calls the constructor, which calls the constructor, and that always leads to a recursive stack overflow problem. So we don't want to do recursive calls inside a constructor of an object. So that's a really bad form. A couple real-world examples. We've got Matryoshka dolls. Great little Russian dolls that nest inside each other. Another example are the computer folders. We can see inside here, I've got folders inside of folders inside of folders, and I can recursively process those. We also have, of course, bowling, because bowling, your score is calculated based on the results of your previous score. So my strike happens after I get a non-strike. Ah, yes. Okay, cool stuff. Now we can take this even further and do some really fun stuff using sorting and searching with recursion. There's a lot of great cool, the idea of divide and conquer outcomes, do some great stuff, make things really easy to solve, and do some really fast time on solutions. And also when you get to advanced data structures, the idea of tree traversal makes things so much nicer because recursion is the way to process a tree. Now I hope this is a quick introduction to recursion. I hope you understand some of the ideas behind it. Again, remember your vocab you want to take care of. You want to have recursion, base case, recursive case, the infinite case, stack overflow, integer overflow because it goes out of bounds too bad, and the fact we can leave breadcrumbs behind to track what we're doing as we go through the stack. Hope this is helpful. Cheers. We'll see you next time and have a good day. Bye-bye.